So it's a great pleasure to be at this nice place. And I'm going to talk about some results on complexity of entangled provers. Maybe Thomas would be a better fit for this type of talk. But at least we have him in the room, and if I say something stupid or you have some questions that I cannot answer, he will help me out, hopefully. So I'm also thanks to John Waters and Richard Cleave, who got me interested in this topic. So we're basically focusing on quantum shared entanglement provers and classical verifiers with exchanging classical messages. So we won't be able to cover this related topics, but I guess for most of them we will have a good coverage later on in this workshop. For example, the session on parallel repetition theorems. And so we give a very quick background of what we will talk about. So we have so two origins of our problem. One is from the interactive proof systems and multi-interact proof systems and PCP theorems that you have heard a little about this in the first talk. And the other origin is from physics side that we study entanglement and non-locality and Bell inequalities. And these two origins combine so nicely in its model where provers are share entanglement and the verifiers remains classical. And motivation for this type of model is one from the interactive proof system perspective view. In that system, we always allow our provers to be all powerful, and it's very natural in the quantum setting to allow this prover to share entanglement. And the other way to see it is it's like a CS approach to study Bell inequalities and non-localities. So I'll set up the problems that we'll be discussing. So although we are also discussing like multi-prover interactive proof systems with multiple rounds, but for most of the time we will be focusing on one-round games, and therefore it's necessary to have some language to talk about it. So in the setting, for example, you have like two provers and shared entanglement. Then the strategy of the provers that can use is first a shared state row, and then measurement. ASA and BTB, we would have the convention that questions were always in the subscript and answers were always in the superscript. And what you really need from the quantum mechanics is this conditional probability. When you have question S and T and the probability that you get answer A and B is this form, this trace row of ASA tensor BTB. And we will use this trace row more in the talk, and it's actually defined as this usual trace form. And we are for simplicity, we would sometimes we always assume that this row will have the same system as the operators are acting on. So sometimes we would omit the taking the partial trace of this state they're using. And of course, what is most important parameter of the games is called a non-local value of the game, and it is simply the maximum that you can achieve with strategy, and this is just an expression of the winning probability, where we were always taking the expectations of the questions and summation of the answers. And so this omega star is the usual quantity that we talk about in this setting, and there's another related quantity called fields value, where we simply drop this tensor here, and we additionally add a commuting condition. So you can see that any strategy valid for this non-local setting, it is automatically strategy for this fields value definition, because these operators always commute. And so therefore this omega f will be larger than or equal to omega star.
Do we have any example where they're different, or we know they're different?
It's an interesting question. And for any finite dimensions, they would always stay the same without.
Are you allowing infinite dimensional spaces?
Yes, we are defining this. Introducing this omega f is only meaningful when you including infinite dimensional systems. Otherwise, it will always be the same as the omega star.
And could it be that like with uncountably infinite dimension, you can do more than with countably
because of the algebra that we're considering is like finitely generated, it will be suffice to consider only countably infinite dimensional systems.
Okay.
Yes.
It's equivalent to an open conjecture operator algebra.
Yes, so we'll mention that later on. So this is like the most important quantity here we will be interested in is omega star, but we will also talk about briefly about omega f. Oh, this is the verifier that we decide whether to accept this question and answer pair.
So it's just 0 or 1?
Yes, 0, 1, and the 1 meaning we accept the answers. So another like simplification of technically assumption is when these games are symmetric, we can always assume that strategies are symmetric. It's kind of a nice a trick, a simplified sort of things. And
So what do you mean symmetric?
For the game, when the provers when the game is symmetric means that we don't actually distinguish Alice and Bob. They would always be regarded as the same.
Is rho the same? Is rho the same up to?
So there are two things. For example, first, if the game by definition itself is symmetric, for example, the linearity test, and then we send a query to each prover and expect answers, and there's actually no difference between them. So then under this assumption, you can assume that the state rho is symmetric and the measurement they're doing is the same. So we will also be interested in a particular matrix norm called rho norm. This rho is a state, and it's defined in this form. And it turns out that this is a very nice quantity to consider in the analytical game setting to argue about the distance of measurement strategies, and most importantly, if two measurements are close in the distance induced by this norm, you can sort of replace one by the other without disturbing the system by much. So this will be the quantities that we will be interested in, and next we'll give you some examples of interesting non-local games that will be give us some intuition of this kind of systems. So the first game that we will be introducing is so-called Mermin Magic Square game, Mermin Pierce Magic Square game. So you have this magic square here where you have 9 variables, and it's 3 by 3. And we use this double line to indicate that the parity of this column is odd, and all other line and columns have even parity. So classically, it's a system that has no solution because the rows give you even parity and columns give you odd parity. And when you have such a constraint system, we consider a game built upon that. And to do that, we sample a constraint and one variable from it. And we send the constraint to the Alice and the variable to Bob. And then we check two things. First, Alice's answer is an assignment for the particular constraint. And Bob is used as a consistent check that this, for example, this x5 is the same as the answer that Alice has given to us. So there are two checks. And classically, without entanglement, this kind of two-prover game would correspond to the certifiability of this constraint system. If there's no satisfying assignment, then provers cannot always win. So we have some sort of soundness in the classical case. And so we call this a magic square game because not only that this omega star, the quantum value is larger than the classical value, but also that the omega star is the largest possible. And as a property, it is 1. So it means that for this particular game, Alice and Bob can always win with actually 2 e-power pairs. And the generalization of this model, you can consider any arbitrary constraint systems with binary variables, and you can define a game upon that. And this is just the binary constraint system games that Richard and Mitchell are discussing in their paper. And for example, you can rewrite any parity constraint as 4 as a formula of 3 set with 4 clauses, right? Each clause will rule out one possibility, and then each constraint is the 4 clause 3 set formula, and therefore the whole system is a 20 clause 3 set formula. And what this example telling us is that this 3 set formula is not satisfiable classically, but actually there's a quantum strategy to win the game that build upon this 3 set formula. And therefore it's meaningful to define a problem called 3 set star. And it's just a game that you consider whether there's a perfect strategy for the prover to win this game with shared entanglement. And the example telling us that this is actually a new problem that other than compared to this classical 3 set problem, because sometimes you have a classically no instance becoming yes instance.
Can you explain 3 set star again?
So the 3 set star is a problem that the input is the 3 set formula, and you have a bunch of 3 set constraints, and we ask whether if you play the 2-player game with shared entanglement, the prover can always win.
A 2-player game of clause versus variable? Or?
Yes, this clause with it's constraint variable pair.
So it's a game.
Yes, it's a game. And now it's defined on the game level, but we'll later see on the more constrained system level. Yes.
Why do you have to? Sorry.
But this game is not exactly a three-set star instance, right? Because if you select a line, you select several.
Yeah, you can. For example, you can consider this instance, and you select only one 3 set constraint. So each one will have 4 out of it, and you randomly select one of them.
Sure. What I mean is doing this is even harder than what would be required in three-set star here.
Actually, for this problem, it's exactly the same.
But
Because
here the prover has to like 4 clauses are selected, and he needs to make 4 clauses true at the same time.
Yeah,
While
but
in 3-set he needs to make 1 true at the same
yeah,
time.
but what this Magic Square game shows you is that actually the provers can always answer with the right parity constraint.
Yeah.
So, and this means that every 4 of the 3 set constraints are automatically satisfied. So,
Exactly. So
yes, yes.
he doesn't, but he achieves more than he would. need.
Yes,
And you can consider the game where you only ask the prover 1 clause. And classically, you can't win that game if it's unsatisfiable by the but quantum you can always.
Sure, I'm just saying it's a harder problem to do Mermin Paris squares than to make a corresponding 3-set star.
Yeah, generally it will be a harder problem maybe, but for this particular instance, they are equivalent.
Sorry, what are the 24 clauses here?
So we have 6 parity constraints, right? Row, column. This you have 6 of them, and each of them can be represented as 4 3-set clause, right? Yes. So you have totally 24 of them, and the next example that we'll be discussing is this so-called quantum 3-current game. It's another classically it's also a well-studied game, and we also study this quantum generalization using a 2-player game. So the game we played is we sample 2 vertices U and V of the graph, and we challenge the provers to give us the colors. And we 2 checks. First is a consistency check. If they are given the same vertex, they should give us the same color. And in the second case, if we give them 2 adjacent vertices and we have to see 2 different colors. This is just very natural a game that you consider on top of a recurring game problem. And so the claim here is that there is such a graph G, which is finite and concrete graph. And you play that recurring game on this game G, the quantum value will be 1. But it's actually not colorable graph classically. And we will call such a problem recurring star asking whether the graph is quantumly 3-colorable. Yes?
Just like you translated parity to reset?
Yes. Yeah, sure. You can think of it as a 3-set problem.
But then, don't you get the same kind of thing for 3-coloring just by a gadget? Translating each parity clause to some coloring thing?
Yeah, so there's, because 3-current is more special kind of constraint, I don't know. Yeah.
Sorry. So This difference has to do with STP solution versus integral solution, doesn't it?
Yeah, you can see it that way.
So then, can you also view, is there anything to be obtained by looking at ways of fixing STPs, going to the next level of the hierarchy or something? Is there a natural interpretation there of that versus the quantum games?
We will see one interpretation in terms of actually we're considering operator solutions of some equations,
Yeah.
and it will corresponding to this decision problem without resulting to a game. It's actually another mathematical problem defined upon these constraint systems and involving operators. So. So these two examples, one's magic square and then the current game, and they're actually what they tell us is that entanglement sometimes hurts soundness. For example, the magic square game that we come up with reset instances where it's actually not classically satisfiable, but we have this when you share entanglement, this interactive system is no longer sound. Because there's actually no soundness at all for this shared entanglement system, and well, this you can think of this as either a bug or a feature in our system, and we'll see for some interactive systems it's actually a bug and a very big bug that we are not able to fix. For studying of multi-prover games is with shared entanglement, the first thing that we understand very well is the two-player XOR games, and it's based on this series and characterization of such games, and actually we can use this result to show that the game value of this two-prover one round with parity XOR game will have a SDB characterization and of expansion size. So therefore, you can show that actually this class is contained in the expansion time, and there are improvement on that result is showing by working on that this class is actually contained in QIP2, where QIP2 is this quantum two-message interactive system with single prover, and this class is intended shown to be subclass of P-space by G.N. Upadhyay and Waterloo. So if you compare it to the classical complexity class, as well from Hassad assumes that this MIP, parity MIP with two players, one round, and at least for some constant soundness and correctness parameters, it's the most general interactive system you can have is in exp. So unless we have that an exp contained in P space, these two classes will be different. And what this means is that actually, for example, you have like an interacting proof system in that sense, and when there's entanglement, the soundness is not. We somehow hurt soundness and make it not a valid interactive proof system, and therefore the complexity class collapse. So, yeah.
What's the best lower bound we have on?
Yeah, I'll get into that. Yeah. So, and the other result is a little bit general than this XOR game. It's called unique game. Unique game in the classic setting is it's a very hard problem, and we don't know how hard it is. And in the quantum case, it's actually an easy problem by this quantum rounding procedure. And you can also view it as an indication that entanglement can cause problems in our interactive proof systems. And these problems are actually non-fixable if you assume some reasonable assumptions on complexity classes. Yeah?
It's funny that you call Gabby bug, because I would have said this is a feature.
Yeah. I would also like that point of view, but yeah, we'll see later on.
What is the bug? I'm sorry, I don't understand.
Who's responsible?
So for example, you have a previously sound system, but when you have entanglement, it causes a problem in your system. So
That's
yes, in that sense, it's a bug.
It's no longer so.
So the next natural idea is if you consider more general multi-prover interactive systems, is it possible to actually control the behavior of the verifiers? And I found this picture very describing our situation here. It's actually a product that you can buy. And so you can think of the dogs as provers, and this product is called a tangle-free dog leash. And this is actually what we want to do here. We want to somehow design protocols for verifiers so that he can control the behavior of the provers, and entanglement between them will not matter.
But these things, they never work, right?
I don't know. So there are a bunch of techniques in this following this type of idea. And for example, we were discussing consistency check and confusion check and adding a third prover. And there are also a private information retrieval idea that will actually allow you to show a low bound on this class that you're asking. So we start with private information retrieval. The idea is that we trick the prover is trying to use the entanglement, but we somehow we actually hide our query to the provers using this private information retrieval scheme, so that they have no idea what we're actually querying. And therefore, you can argue that entanglement won't help you much, and therefore you have this lower bound. And so in following, we'll discuss this other three techniques used in restricting the role of entanglement in multi-prover interactive proof systems. So first, the consistent check is simply that we send each prover the same question, and we expect the same answer from them. And so we already see this two-prover consistent check for example, in the three current game. And somehow it tells you that it's not quite strong enough to actually control the behavior of the provers to show entanglement, because in the three current game, we still have this strange behavior that causes a bug of our system. But depends on, I guess it depends on what's the original protocol is, and it is an interplay between the original protocol and the consent check they are adding. Maybe there are some other systems where a two-player consent check would also allow you to limit the entanglement. So there's also like three-player consent checks used in, for example, the linearity test and multilinear test. Actually showing breakthrough result for the lower bound on MP star. And another use of this three-player consent check is in the paper by Ito, Kobayashi, Prender, Suen, and Yao. They actually used this add this check consent check to the so-called PCP simulation test, where the three-query PCP procedure are simulated in the system. So the consistency checks are not only as a sub-test that we use, and also very important concept in defining and improving these theorems as a measure of closeness. And we will use this. So what does it mean? So we define this concept to measurement as a probability that they will have the same answer, and the inconsistency as they give the different answers. And the importance of this thing is, first, it's very easy to analyze. You get this kind of quantities right on the structure of the game. And the other thing is that you can prove something like this, where this distance between two measurements is somehow bounded by the inconsistency of A and B. And if you can argue the distance, you can argue this inconsistency between A and B, you have a bound on that, and you can use the place of prover argument. So the other check is called confusion check. It's quite similar to the consistency check, but this time we would trick Alice. We don't tell Alice what is the actual question we are doing consistency check. And so we sample a pair of questions and send this pair to Alice and one of the questions to Bob. And we check that whether they give the same answer on this particular question Q. And you can use that. Actually, this kind of technique is used to show that it's hard to compute this entangled value up to an inverse polynomial precision. And this is a lemma showing here why this kind of test would be helpful. Essentially, if you have a high success probability winning this confusion game, then you have structures on Bob's measurement. It's kind of a commuting constraint. So for example, if
this applies to the magic square game too.
Yes.
And so the lemma that these bounds you show do apply to the magic square game.
Yes. And in the original Magic Square game, we actually don't have this confusion check. If we added this confusion check, we will fix the problem.
I see. Oh, it's
Yes.
unordered.
Yes.
Okay, so I guess the confusion test is unordered. So
Right. You don't know where
So-
the other guys figured
Yes.
What was the magic
And we will see so why this check is useful, and we have a more clear picture in later discussions.
So I didn't understand what should so suppose you give Alice Q and Q prime.
Yes.
What should her answer be? Let's pick an example as the magic square game. What's Q and Q prime, and what's her answer should be?
Well, the answer will be to think of it as what's the assignment of the variable of xi of an xj, and you should answer 0 or 1 for each of the variables. And yeah, that's the question.
So you're asking
a pair of variables, and for the other player, we only ask one of them.
Either 2 rows or 2.
So it's 2 rows in the case of the magic square game?
No, 2 variables. Yeah.
It's kind of strange because you're asking pairs of variables where originally you asked for 3 variables.
Yes.
So
But sometimes you ask Alice for 2 variables that might be different rows.
Yes.
And sometimes you ask
That's the
her
idea.
for a row.
Right. So
And Bob's always gets a variable, right? So Bob
Yes.
doesn't know.
yes, that's correct.
So the confusion test does sometimes ask the normal question and sometimes ask Alice 2 Bob questions. Is that
Yes.
what you're saying?
Yes.
Okay.
So another technique is simply add a third player, and it's well-known property of monogamy of entanglement, where it basically says that if Alice is highly entangled with Bob, then her system cannot be entangled highly with Bob prime, and so you can use this type of argument by adding a Bob prime and doing exactly what Bob's supposed to do, and you can use this type of argument to show the hardness of 3-player games. And actually, you can see easily why this works for like Magic Square game, because Magic Square game you have 2 EPR pair shared between A and B, and if you also allow Bob to A and B prime to have the same property, then Alice will have trouble because she won't know how to share the EPR pair between B and B prime. And you can also use this kind of argument. And this time with we randomly choose 2 players out of 3 players. Classically, it's kind of nonsense, but quantumly it works sometimes. And actually, this is what Vedic did in the low degree test. But I guess we don't know whether it's actually needed. But currently, it's how it is proved.
Same it for the magic square, you do know that it's needed.
Yes, you can actually see. Yeah.
This and also the confusion when you take the magic square game.
Yeah.
You have this perfect strategy that wins with probability 1.
Yes.
This will make this question also. If you change the game a little bit,
Yes,
you
yes,
play the magic
yes.
square game,
Yes.
then either you do this 2 out of 3 version of the magic square game,
Mm-hmm.
or you keep 2 players but you add this.
Yes,
confusion.
yes,
Then
exactly.
suddenly
Yeah. Yeah. So all these techniques can be viewed as how you can fix a problem that the entanglement has caused in our system. Maybe I don't have enough time. I'll skip this slide. So basically, you can use this type of techniques to prove that it's NP hard to distinguish these two cases, either the omega star equals 1 or it's at most 1 minus 1 over polynomial. And the argument that we use is simply the so-called state invariance lemma with Bob prime technique, because the state here is simply the post-measurement state when you do BQ measurement, and the distance is somehow bounded by the self-consistency of the Bob's measurement. And when you have this type of theorem, one idea to round it to the classical strategy is you repeatedly measure the state with different measurements, and you would somehow get answers. But of course, the problem is we have like bad soundness in with this type of 1 over some polynomial, and if you scale it up in MIP star, it will show you some containment of an X with especially small soundness correctness gap. So the next result that we'll be spending more time discussing is this nice lower bound on MIP star. Actually, it proves that MIP star equals an X, and an S space is contained in MIP star, and you can think of it as our bug being fixed for all protocols. Any classical interactive proof system, interactive proof systems, you can modify it and so that it becomes entanglement resistant, and actually this is best we can hope for using this type of entanglement resistant techniques, because the idea is to restrict the use of entanglement, and the best you can hope is prove that the classical interactive proof systems is contained in MIP star.
Does that cost you extra provers to do this procedure?
But yeah, this class is fun is polynomial many provers, so we don't care. Actually, it's
that's the definition of OIP.
Yes, yeah, sure. We don't care how many provers. But actually, there's a question. We now probably only be able to show that three players can contain an X, but we don't know whether two players can also be proved. I guess so, but.
Could you explain your second point? So what does it exactly mean? You can modify it. So
So this is. So obviously there are some multi-prover interactive proofs that are not so good when there is entanglement, right? So but what this style shows that if you do this machinery of using polynomials and doing multilinearity tests, then actually this is a different proof system of the same problem, but now you can prove that it's entanglement resistant.
And that means it has the same value?
Yeah, approximately the same value.
Okay.
Yes.
In a weak sense, you think if it was 1 before, it's still 1.
Oh, okay.
And if it was not, then it's
0.9
or something.
And those,
Okay, fine.
those modified provers, are they still in the honest case classical, or do you need quantum?
The provers are quantum. They can show entanglement and can show that.
No, I mean the honest provers. I mean, if you want to.
Well, for honest provers, yeah, you can win it classically.
So you achieve this. So the protocol, the secure protocol is a classical protocol, but that is secure against quantum provers.
Yeah, you can see that. Yes. The proof of this result is followed quite closely to the classical proof of containment of the next in MIP. And basically, what needs to be done is that the multilinearity test is sound against entangled provers. And what we mean now by the multilinearity test, you consist two tests. One is consistent test, and the other is ordinary multilinearity test, which is essentially the axis aligned linearity test. You choose an axis and sample 3 points and see whether the answers are linear in this on these 3 points. And classically, the proof is basically you can show that the provers will be forced to use a common multilinear function to answer your questions. And quantumly, it's even not clear how such a statement would be formalized because you have like measurement operators given this x, and you measure and you get some answers, and what does it mean to be close to some multilinear function. And this is how they find this solution. And it says that actually there exists a measurement Vg where it doesn't look at the input of the x and any queries. You just measure and get a multilinear function and the answer with this multilinear function. So this is basically the claim. And if the strategy of AX, we are using this symmetric assumption, so AX would be ABC's strategy, and they win this game with in both consistent tests and the multilinear with high probability, then you can prove that you can replace this V measurement, the original AX measurement with something VG where it doesn't really depend on X at first. First measure a G and then use this input X and obtain the answer. And once this is obtained, then you can replace the AX with V's and essentially we will have a situation where players actually sample this same multilinear function to play. And so this is what Zuishi and Thomas showed in the paper. And the way that it is shown is this kind of induction on number of variables that we can depend. We remove the dependency on the measurement of the variables one by one. And in the proof, what technical difficulty is that when you do that, the error in terms of inconsistency grows exponentially. And you sort of need a consolidation step, and which uses SDP. And the structure of the proof is quite similar to the classical one, but the consolidation step is rather complicated and technically, and actually you have to do something active change to a measurement to achieve such statements. So unfortunately, I will not be able to tell you more details about this main step, but will give you some flavor of how techniques are used in the proof by introducing the induction step, where we simply remove dependency of one variable. So what is the statement? We will find a measurement that only depends on n minus. So the X is a tuple of elements from F, where this X negation I is the string where we just remove the ith element, and therefore its measurement doesn't look at the ith coordinate, and it gives a linear function as a result. And the way that this is played in the game is first you do this measurement, and then you use this linear function applied on xi and get result. So this is basically what the induction initial step that we are doing. And first, how do you come up with such a measurement? You only have like a measurement give you x and give you a result, and now you cannot depend on this i's coordinate for some random I. And the way that they come up with the solution is you just choose two random points on the i's position and then do the measurement, and you give you some result, and then you just define the line to be the line that going through these 2 points. So this is how this measurement come up. And so we only need to show that for this particular measurement, you have this kind of statement. And the proof is really about controlling the errors. So the first step is simple. You just expand the expression bx here, and you get a huge expression here. It's like a trace through of 3 tensors. And this one is simple because the summation of i's gives you identity. So the first approximation that we will use, we restrict the a prime to be one particular value of that you can have, and the intuition is from the consistency check, because in that part we already measure ax prime and get result l xi prime. So by the consistency check assumption, the only main contribution that when the third player is measuring is getting this result. So up to some error epsilon, you can drop all other a primes. This is the first step. The second step is a little bit more complicated, but the idea is very simple. We just simply want to remove these two terms here. And why you can do that is actually an argument of we have already seen. It's called state invariance, because measuring this or not doesn't really disturb the system very much. So you can remove it, and up to some error square root epsilon, you have this kind of result. And then you just remove this inequality here. This happens with the equality only happens with 1 over the size of the field. So it's also small when the field is large, and therefore you have this here. And finally, this is simply the assumption on the multilinearity test that you have. So finally, you get this assumption that consistency of A and B are high, and therefore they are close, and you can replace it. So this is basically the proof of the first step, and it actually gives us a nice lower bound of MIP star. So what about upper bounds? Unfortunately, nothing concrete is known. And for example, you can use random projection approaches to somehow reduce measurement dimension, because we don't have a bound on the shared measurement that Alice and Bob can use. And if you can bound dimension, you can have at least some up bound, but it doesn't seem to work. And there's a nice result using non-commutative positive Lenses, which essentially give you a STB hierarchy that you can approximate this omega f from above. And it's also trivial to see that by increasing dimension larger and larger, you can have an algorithm to approximate omega star. But the question is with whether these two are the same. If it's not, then these two algorithms cannot combine to an algorithm to decide to approximate either this one of them.
Sorry, what happens if they're the same? I don't understand. What does that
If it's the same, then you can combine these two algorithms to at least show that these quantities are decidable. Yes.
But that's the
Yeah.
nothing more than decidable.
Yes, I guess nothing more, because we don't know how far these two are converged. Is that correct?
Well, then you should probably add the name of Lava.
Settled the whole. I mean, he really proved that the problems are completely equivalent.
Okay.
Yeah.
Oh, I don't know that they are
And,
completely equivalent.
I mean, we would be even happy to know whether the con embedding problem is decidable. I mean, at the moment, we just don't know anything.
Okay.
It's
We don't know anything. What?
whether con embedding problem is true. That's a big problem in non-operate. I mean, one of the three biggest open problems on operate algebras, where just nobody has a clue. Period.
Can you say what the problem is?
Every hyperfinite factor is embeddable in the ultra product. Every 2-1 factor is embeddable with the hyperfinite factor, but it's equivalent to having matrix models. If you ever heard something about free probability in matrix models, that's where it belongs to.
And what would it imply, even if...
So if the constant embedding conjecture is true, then these two are the same, then we have at least some decidability.
No, it's if and only if. I mean, if these are the same, then con embedding is true and vice versa.
Okay.
That's Ozawa.
So con embedding is the statement that these two are the same.
Con embedding is a problem.
Well, actually, can you say again? So, how you define these two in terms of, is it a supremum or in dimensions, or is it defined directly? You said if the two quantities are the same, then this is equivalent to con's embedding.
Yes.
Node. Can we say again what the quantities are precisely? I mean, I know omega star and omega I.
Okay, so the difference is that omega star is calculated by looking at POVMs, which are infinite dimensional and tensor product position. whereas
And
omega
tensor
star,
product.
tensor product position, whereas omega f just allows arbitrary infinite dimensional operators which commute.
Okay,
So whether every commuting family can be approximated by a matrix, I mean approximated in some sense by commuting matrices, which then necessarily have to be in tensor product position, because in finite dimension commuting means tensor product position.
Right, so that's
Yeah.
so the difference that omega star is defined as a supremum over increasing dimensions, whereas omega f you define directly.
Directly, yeah.
Over infinite
We
dimensions.
don't think about the SDP hierarchy, but okay, that's okay, I guess.
So now we somehow get back to the question of whether this kind of magic square games are indeed a bug of our system. One reason is with this entanglement resistance technique, we can only show like lower bounds, and there's no hope that we can show something outside of MIP to be inside this MIP star. And one interesting direction to look at is this. We don't add this additional checks to enforce the behaviors, and we just let dogs do what they would want to do, and see what actually this class would give us. And to start the investigation, it's quite natural to at least ask what's the exact case complexity of this kind of problems. So, for example, we consider a binary constraint system game, and we simply ask when would the provers will have a winning strategy in the quantum sense. And this is a nice paper by Richard and Rajat saying that if and only if when the corresponding constraint system has so-called quantum satisfying assignment. So what is a quantum satisfying assignment? It should be some sort of assignment, but it's quantum. And the way we define it, first you transform a constraint system to constraints of polynomials, and we only require that. So the polynomials, the roots of polynomials on the Boolean cube will coincide with this original constraint, and you can always do that. And then this quantum satisfying assignment is simply assignment of operators, matrices, finite dimensional matrices to the variables, and they are self-adjoint in Hermitian matrices. And what makes them assignment? First, when you replace these variables with matrices, you get an identity of a matrices. This is quite natural to assume. And the second condition is simply the binary condition that we have for the variables, is x squared x to x. Now, the third condition is kind of interesting. So it says that in order to be a satisfying assignment, each variable xg and sk occurring in the same constraint must be commuting. And this is technically a necessary condition because you want to replace variables with matrices, and polynomials are commuting, and it doesn't make sense if you replace a non-commuting matrix in these polynomials. And I guess it's a more deeper reason is Alice's are given constraints and are allowed to asked to do measurements using these operators, essentially. And the commutativity of the matrices allow her to actually observe all the quantities simultaneously. And otherwise, for non-commuting matrices, there are so-called uncertainty principle, and then you won't be able to observe all the variables you want. So this condition is kind of interesting, and we give it a name called locally commutative condition, and simply says that every variable on the constraint should be commuting. So once we have a quantum set definition of a quantum satisfying assignment, we can ask whether a constraint system is quantumly satisfied, a new definition of satisfiability, right? So let's review this concept using the magic square game. The magic square game has indeed a quantum satisfying assignment in this form, where these matrices are 2 by 2 poly matrices. And we are cheating a little bit because these are square 2 identity matrices, but we are working on plus minus domain, and previously we were talking about 0-1 domain, but it doesn't really matter. And you can check that every row will have matrix product 1, and this column will have matrix product -1 identity. And one observation is actually found by the local commutativity condition, every operator on the same row or column will be commuting. And another observation is that any two matrices not on the same row or line column, they will be anti-commuting. And this is for this particular solution, and you can actually prove that for any solution of satisfying assignment of the magic square game, it will always be the case. Any two variables not coming from the same row or column, they must anti-commute. And you can use this as a gadget to actually glue this magic squares together and prove some entanglement lower bound using a representation series of Clifford algebra.
So is there any relation on the dimension where this operator live and the dimension of the entanglement you need to...
Yeah. So the sizes of the matrices
Yes.
is just the dimension that you want.
Okay.
Yeah. So let's test your intuition of what we are defining as a quantum satisfied assignment. We add a trivial constraint, which is f depending on x2 and x4, but it's actually always accepting. It's always true trivial constraint. So what does this system mean? We have like this 6 constraint and then this one additional trivial constraint. F is always 1, always satisfied. But artificially, it depends on the two variables. And it doesn't make sense for classical problems, but we'll see if we translate this to a quantum game, then actually what you would be doing is Alice is send two variables, and Bob is send one of them. This is what we have already seen, it's the confusability check, right? And by definition of quantum satisfied assignment, what you will see that now this new constraint system doesn't have a quantum satisfying assignment because we say that any two x2 and x4 must be assigned anti-commuting variables. But now this trivial constraint will actually enforce x2 and x4 to be commuting, and therefore there's no operator solutions to this new system by adding this new constraint, although it's trivial. Right. So this kind of argument can show that original 3-set star with some sort of trivial function constraints will give you sort of this kind of problems are NP hard using your Thomas give argument in months ago in this place on adding this confusion check and consistency check to this will give you some hardness of this thing. But yeah, this would be another view. You just add this kind of trivial constraint. It's not quite like a 3-set constraint because you cannot actually represent it as a 3-set. But this is how these are connected.
You showed how to do this with 3-set.
Sorry?
You're going to tell us.
Sorry?
You showed how to do this with 3-set.
You should how to.
You yourself.
Well, I mean, the results that you have a gap. That yeah. So another thing that is natural to consider is we now have the new definition of satisfiability problems called star problems, and it's whether the problem is whether you can reduce one to each other, and it's nice to have, and the idea is that it's actually possible. We actually can do that from taking any arbitrary classical reduction and add some gadget on that. So. And the problem that we will have is if you have this 3-set system will have a quantum set assignment where you can either come up with this coloring measurement for quantum 3 coloring game because of the local commutativity condition of the operators, but on the other direction it's kind of harder to all right. So in the other direction, we have problems. For example, you want to read off the operator x1 from this node and x2 from that node, then we don't know even whether they are commuting or not. So we designed some sort of gadget using graph constraints and show that for this particular graph, which is a triangular prism, and the claim is that any coloring measurement for A and E will be commuting, and this is only constraint on these two nodes. So, and the proof of this only condition called extendability is this kind of classical thing that's easy to check. And to establish commutativity, essentially you are trying to say that the commutator of these variables are in the ideal generated by the coloring constraints, and these ideals are, and the rings are non-commutative. So generally this ideal membership problem is undecidable, and for this particular case, you can use some techniques from non-commutative Grosvenor-based computing to assist the proof. And once you have this gadget, you can recover the reduction by assigning by connecting identify this A and E with to any two vertices you want to the commutativity between them. So the commutativity gadgets for some problems are actually very easy to construct. For example, by using local commutativity condition, this would be a 3-set commutativity gadget for 2 variable x1 x2, and so this is how I previously showed that 3-set star is NP-hard, and actually what this is doing is actually another confusion check in disguise. Because this y variable is a new variable, and as Bob always know that you can assign it to 1 and without loss anything, and when you sample this kind of constraint, Alice is essentially given 2 variables, and Bob is one of them, and this is another confusion check that you will be due. And therefore, you can actually embed all this confusion check and constraint check inside of the constraint. So you actually do not need this kind of additional constraint, and see that this 3-set star is NP-hard even with some gap. And of course, the problem is that we don't know is how hard exactly this 3-set star. And the difficulty comes in because we don't have a bound on dimension of the operators that we are seeking for. And I guess if it's interesting to have what we are discussing now is the exact case hardness. If you can come up some ideas to relate this to approximate case, then something interesting would happen. So to summarize, we can have sort of non-local NP theory, consider a lot of star problems, some from satisfiability and some from graph problems, and we also can see that these 2 problems, 2-set star and 1-set star, are easy, and we are sort of the situation where we can establish a non-local Schiffer's dichotomy theorem, but there's a little problem of the affine-set star where you have constraints of the parities like the magic square, and we don't know how hard this kind of problem is. It's not shown to be hard as hard as 3-set star, and it's not known in P. And only for some subclass of this game we know that it's easy to handle by Alex Arkhipov. And it's an interesting connection to graph planarity. So I guess the question that also a problem that we have for this BCS problems, star problems, is they always use EPR pairs in the perfect strategy, and it's kind of a good thing for having a simple structure, but also a question whether this is a special cone orbit that we are looking at. Is it as general as the exact case Hardness, because we always involve that EPR pairs. So I would quickly go through the sort of ideas on how you can actually define, well, yet another quantum PCP theorem or conjecture. We have a famous one in Hamiltonian complexity definition, and I guess on the game level you can also consider like the hardness of approximation of non-local games as a definition of a quantum PCP, and you can say whether a constant approximation of mixed size NP-hard as a version of PCP theorem, and this is actually achieved with 3 provers, but maybe there's because this kind of omega star, the hardness of approximating that, and the class of NP star, we actually don't know what actually hardness is. So maybe it's more safe to claim a PCP theorem as a self-contained statement, whether the approximation of omega star is hard as exactly determine the value is 1. It depends on how you see the problem, and you can also sort of define PCPs based on more a proof verification style, and have some restrictions on the proofs that are non-local conditions on proof string, and from this magic square game, and it seems like also a possibility to use only one prover, but restricting the case where when they ask the queries must be commuting observables. So it kind of might lead you to a different definition of this nice conjectures. And this is what I will say, and thank you for attention.
Are there any questions? Do you have an upper bound on the dimension you need, depending on the number of questions of these games, or questions, I mean, number of?
No, I don't.
So it could be that with this type of games, you get.
Yeah, it would be nice. Then
you have kind of a game with a constant number of inputs and outputs, for which you need unbounded dimensions, so infinite dimension to get the optimal strategy, or.
We don't have such examples, but
they could exist in principle.
Yeah, it could exist in principle, but
yes.
Okay.
Yes.
Yes.
Can you explain why the feature? I understood the bug. I don't understand the feature.
The feature. Well, the feature is this kind of games are. So why does it bug? Because we are thinking of it against the classical satisfying problem, right? And what we are arguing is actually this is discussing of a new kind of satisfiability problem. It's called quantum satisfiability problem. And for that problem, it's not a bug. It's a kind of new kind of problem that we are studying. It's kind of a feature of the system. And is that argument satisfying? Because if you consider that you stick with classical satisfying problems, then obviously the entanglement comes in and causes problems. But actually, what this kind of two-player games are studying is a new kind of satisfiability question, and you cannot say that it's bug for that kind of investigation.
It's a feature because it keeps us off the streets, right? Okay, so maybe we should wrap it up, and it'll just be a short break. We'll reconvene in 8 minutes, I guess. Just stretch your legs, and it'll be not a talk, but kind of a discussion session, and it'll actually continue on some of the same topics. So let's just have a short break and come back. And let's thank Zhengfeng again.